Kia ora, good afternoon everybody. My physics class is on the 11th of May 2020. Today I want to look at, that's that done, and that I want to look at curved mirrors. We have looked at plane mirrors made from flat sheets of glass with silvering on. We'll look at curved mirrors. There are two types: concave, those that bow in; convex ones, those that flex out. How they are built, two types. How to get an image, three very handy rays, because there are gigajillions of rays made. Jillions is bigger than zillions, and giga is a billion of those. Three very handy rays that help you answer exam questions and figure out what's going on. How to get an image from a convex lens. I'll do concave next time. What the image looks like, and I'll do an example in a separate video from a soon-to-be set bit of homework on page 29, question 4. Alrighty, moving along. That's the homework we've been working on. These should be set in. Basically, this is all waves. You should be well underway. This stuff is now overdue. This stuff is coming up very soon. You're doing a great job overall, guys. I'm really pleased. Homework marking, mark it a 5. Cool. On page 25 of Dave Houston's workbook, which looks a little bit like that, and we've been using it a lot. Curved mirrors can be made by taking a chunk of a glass sphere, glass ball, silvering it on one side or the other. That's the cheap one. So that's the type we're going to be doing, because they're actually simpler to figure out. We've got the center of curvature of the ball, and the P is the pole. That's the middle of where we're looking, where the mirror is, because it isn't a whole big ball, it's just a chunk of it. That's the middle of it. And that's for a concave mirror, center and the pole. And the convex, well, it's basically the silvering's on the other side, no problem. Parabolic mirrors are more the type used in headlights and super expensive astronomy ones, because they're slightly more perfect and a heap more complicated to deal with, so we're not going to deal with them. Some handy bits of naming we need to know. Couple of things. First of all, if light rays come in parallel to a curved mirror, we would have done this at practical if we had the lab open. They all bounce back through a fixed point and that sort. Or if we come into a convex, they look like they have come from a fixed point. Some key buzzwords. First of all, the C is the center, F is the focal point, P is the pole. These three things in purple are positions, places, points. These two things, F and R, are lengths. They are focal lengths. And oddly enough, in physics, optics is the only time in this particular stuff where we actually do deal in centimeters. Normally it's just millimeters or straight meters. So, focal length, radius of curvature, numbers, C, F, and P, places. Now, a handy little thing we can stick in the back of our brain. Because of the equal angle in, angle out and stuff, you can prove that the focal length is exactly half of the radius. That's a handy little thing to know. Three key ways to describe an image. It's either virtual or real. Real, the light rays do cross, or virtual, the light rays will never cross, but they look like they might have once if they had carried on a straight line. Is it upright or inverted? That makes sense. Is it up the right way or upside down? Magnified or diminished? Made smaller, made bigger. There's a couple of other cases. A fairly rare one, could be the same size, that's why I've made it in thin writing. And in one very particular case, the image might not be existent. The image might not exist, and we'll get on to that. Here's page 26 of this book. Some handy rays we need to know. If a ray comes in parallel to the parallel to the principal axis, through the center, through the focus, through the pole, or parallel to it, it will bounce back out along parallel to the principal axis. That's convex. If it comes in, it'll come out like that. By the way, we're only dealing with convex. I will deal with concave to come later on. These things are also reversible. It might come in this way and bounce out, or it might come in this way and bounce out. That's one. So that's two rays. They're reversible. The other one is equal angle rule. At the super duper small place where the light ray hits, it's a bit like a little miniature flat mirror there, so therefore angle in, angle out the same, equal angle. That's very, very powerful. A couple of things we need to look at. Reflections must occur at the mirror. There's the mirror, the reflections occur there, not there, not there, there. And I'm going to deal with the normal through here. The rays do come in here, they do go out. Where rays do go, you draw a solid bold line. Where rays look like to your eye and your brain where they might have come, the rays do that, but they look like they might have come from here. Okay, it's cool. Concave mirrors, we'll get to that. Convex mirrors always form images that are diminished, smaller, upright, up the right way, virtual, in behind here. You'll always see an image in there, like the picture that you see on a rear vision mirror that's bulging on the side of a vehicle. Cool, so what I did is I did that and that. I've introduced that, talked about how they're built, how to get an image, three very handy rays, in parallel, out away from the focus, in towards the focus, out parallel. This is for convex. In at the pole, out at the same angle. How to get an image from a convex lens, how it's formed, they cross over. I'll do an example of that shortly. Three key descriptors: real, virtual, upright, inverted, same size or smaller. I'm going to be setting some homework for the soon to be done homework, which we will tackle in the next video, or the one after actually. Cheers guys, thank you for looking, thank you for your time, I appreciate it, and I'll give you a hand with another video shortly on this question here.